Okay, folks, before we get into processing the tensor test data, let's talk about this ASTM standards. Many of you found it difficult to get hold of these ASTM standards and download them. I do not understand why. They are easily accessible through the library databases. In any case, let me show you how to do it. So I'm going to fire up my browser. I'm going to go to, uh, let's start with library.rit.edu. We are going to go under search collections, go to databases, type ASTM standard in the search box. It gives us one result, that is our ASTM standard library. Now, in my case, it did ask me for login, but probably since I'm doing it second time, it didn't ask me to sign in. And I just type E8. So E8 is my standard that I want. So here we go. You scroll down. Here is the ASTM E8 standard, and you can download the PDF, which I have done so. I don't want to download it again. Let's suppose you wanted to find other properties. For instance, soon we would be looking for properties of our aluminum alloy. So let's type aluminum 6061. So for aluminum 6061, it gives a standard specification for aluminum and aluminum alloy sheet plate metric. So again, here I can download it, and this will contain the data I am looking for. So I'm going to talk about this later on. Again, I've already downloaded it, and we are going to search through the data there. Okay. Okay, so we are ready to process our tensor test data. So I have my spreadsheet here all set up. If you want to follow along, please have it set up. Remember, we collected our data in form of graphs. So this is my red curve. It doesn't show up in the camera. This is the green curve. These are my two original samples. These are the broken samples. My numbers may not match quite exactly what are in the slides before because I've got data from different samples. So I've got these broken samples, and I am ready to enter the data. So I'm going to fire up my spreadsheet. So here is my spreadsheet. So we have used this Instron machine. We are going to talk about Rockwell hardness later on. The software is MTS Testwork 4. I have these two samples. This is annealed red aluminum sample. The green one is precipitation hardened. So let's start entering data. So the thickness was 0.059, width 0.5, length 1.97, load 225 at yield. Maximum load was 531. After it broke, I used the vernier caliper to measure the thickness, 0.045, the width, 0.423, and length between the gauge marks after fracture, 584. So this was for red samples. For green sample, 0.062, width 0.504, length between the gauge mark 964. Here our yield load 1450, maximum load 1512. Then I measured thickness using a caliper, width, and distance between the two gauge marks. So just like I am filling in the data here, I'm going to give you this data for your two steel samples. Remember that we are measuring all of these dimensions to thousandth of an inch. So let's display 3 digits. Loads we know only closest to a pound. So we are good there, no decimal digits. And all these dimensions to 3 decimal digits. I'm very particular about number of digits being displayed, so please be careful. Okay, so now we are ready to calculate our properties. So original area would be thickness times width. Final area would be final thickness times width. Elastic modulus. Now this is measured by the machine. We could do much better, but I just let the machine measure it, and I'm not very concerned about elastic modulus. But yield strength. So it'll be loaded yield divided by original area. Tensile strength, maximum load divided by original area. Okay, before I do that, let's calculate both of these areas. Let's copy the formula over. We want to copy formula only because I don't want to mess up all my borders and all that. Elastic modulus was 10.18. And again, I'm not very concerned about it. We probably could measure it better. All right, yield strength. We'll copy the formulas a little later on. Let's go ahead and do others. Okay, percent elongation to failure. So this is final length divided by original length minus 1 times 100. Reduction in area. Remember, reduction in area, we wanted a positive value, so we'll do 1 minus final area over original area times 100. Okay, and then ratio of tensile to yield strength. So we'll take all of these formulas, just copy formula only to these cells. Okay, again, we want 3 digits here, which we have. Oh, sorry, 4 digits, 3 significant digits, but 4 decimal digits, sorry. 4 decimal digits. We want 2 decimal digits here, no decimal digit here, and no decimal digits. It depends on the value. You want to show a couple of significant digits. Same here, couple of significant digits. Okay, let's look at published properties. So for published properties, we are going to go look at that ASTM standard B209M14. So if we keep looking down, so you can see there is a table of values for non-heat treatable alloys. We don't want that. We want keep scrolling down. Here, table 3, tensile property limits for heat treatable alloys. So notice they have got the alloy with the heat temper, heat treatment. specified thickness. Okay, so from 2. Tensile strength, they have two limits, min and max. Often they state one or the other, but sometimes they state both. Same thing for yield strength. And then we have this elongation. Okay. So we search through our properties. Here is 6061. So 6061, T0, this is the minimum maximum thickness. Remember, our thickness was 1/16 of an inch, which is like 1.6 millimeters. So we read 1.6 millimeters. So we see that there is a maximum tensile strength, 150. This is in MPa, maximum yield strength. And then this is elongation to failure. Then for T6, we come here, again, we look through our thickness, and we have 290 and 240 and 10%. Okay. So we are going to enter these values. Notice it didn't show us elastic modulus. Elastic modulus is 10 million psi. Okay. And my source here is, I went through another book, and let's see what I want to show as my source. My source was table 3 of ASM Handbook, Volume 2B. So wherever you are looking properties for your particular material, you have to find the standards, and don't just Google it or something like that. Right now, we did it from ASTM standards. This was B209M14. Okay, so we found yield strength. I've converted it in PSI, and it is 12,300. Tensile strength, 21,800, 16%. Okay, here we have 34,800, 42,000, and then 10%. We didn't have percent area reduction listed there. Strength ratio, we can calculate this divided by that, and same thing here, this divided by that. Okay, we got the other two values from same table. So let's color them red so they highlight. Okay, now I want to mention again that these were the maximum values, right? So let's put a comment on it. And so was the next value, maximum value. So we want to copy comment. And we can see that our measured values were both within this limit. Now these two were minimum values. So we'll copy this comment. And you can see, since both of them are minimum, our measured values are more than that. And these are usually minimum values as well. And you can see both of them, our measured values are greater than that. Okay, all right. Okay, so now let's calculate percent difference. So our percent difference is going to be measured value divided by expected value minus 1 times 100. So we are going to copy this formula here, 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 here. And we'll paste these formulas. And of course, we don't want to show more than one digit or so. So let's format it. Okay, here we go. So let's see. Elastic modulus, even though we have a 10% error, usually within 5% is what is expected. In material science, we are not very concerned about elastic modulus because when we do heat treatments, elastic modulus should not change. So elastic modulus does not change after heat treatment. And really to measure it within 5%, we need to align our extensometer well, and we have to be very careful with data processing. So right now I picked up both of these numbers from whatever the machine gave me. I'm sure my alignment was pretty good and I can get better results. In any case, notice for 6061 annealed specimen, both our strength values were lower. The reason is when it is annealed, we want it soft. So that is why they specify a maximum limit. And of course, ductility is higher. Specified was 16, we got 31. Now, for hardened specimen, they specify minimum properties. And you can see we exceed both the yield strength, tensile strength, and of course, ductility. Now, you might want to think of other things that I'm not mentioning here. So think about it. But let's look at our curves. So when we look at our curves qualitatively, so here is our curve. And remember, this is for red, this is for green. So qualitatively, you can see green is much, much more stronger than red. Both yield strength and tensile strength, much, much higher. Elastic modulus for both is about the same. The slope is about the same. And of course, when we precipitation harden from red to green, ductility decreases. Strength increases, but ductility decreases. Right? So we have same elastic modulus, higher yield strength of green because it is precipitation hardened, lower ductility. Also notice that this curve is essentially horizontal. That means it cannot be strain hardened much. We talked about strain hardening. Remember, as we keep plastically deforming the material becomes stronger and stronger till it cannot deform uniformly anymore. So you can raise the strength up to about tensile strength or so. So you can go raise the strength from yield strength to tensile strength. So that is why the strength ratio is important if you want to strain harden something. So again, I've left you some things to think about from your results for your report. But this was the effect of dispersion hardening because my set of specimens are aluminum, where the difference was precipitation hardening. Okay, so we want to learn more about strain hardening. So you may remember that on our tensor specimen, we had made pen marks about quarter-inch apart from either end, both ends, on both of these red and green samples. So after now deformation, we made hardness measurements at these dots. So what we want to do is we know that the most strain hardened spot would be this. And as we go to the left or to the right of this failure edge, it would be less and less strain hardened. In fact, in this grip area, we should see the same hardness as we would see on these three dots. So I have got three dots very close to the edge where it is in grip, where we have measured those hardness indent. So that would be hardness of our sort of original samples. So anyway, in last lab, we had talked about Brinell hardness test. Now, Rockwell hardness test is probably the most common, most popular test. It has got many, many scales. It can be used, the regular Rockwell test can be used for thick specimens. There is a superficial Rockwell test that can be used for thin specimens. In fact, we are going to do superficial Rockwell hardness testing on our two samples here. We can do micro indentation hardness test, which is even on a much smaller scale. So we already went through theory of Brinell hardness testing. In the next lab, we are going to talk in more detail about Rockwell hardness test. Right now, I just want to use it as a equipment to get my hardness measures. Just to give you a kind of scale, remember we did Brinell testing, and for Brinell testing, this is what the indenter looked like. So the indenter holds a 10 millimeter diameter tungsten carbide ball. I have this replacement ball here. So in case this gets deformed, I can replace it. Now, the load we used in Brinell hardness testing was somewhere from 500 kgs to 3000 kgs. More common was around 1500 kgs. In Rockwell test, which we can use for both soft and very hard materials, we use loads of the order of anywhere from 15 to 150 kgs or so. So the most common scale for thick specimen is B scale. So B scale is used for soft and non-ferrous alloys. So if this was a thicker piece, then I would have used a 1/16 inch ball indenter. So the 1/16 inch ball indenter looks exactly like Brinell, but much smaller in size. If I had very hard material, I would use a C scale. A C scale has got this conical diamond indenter. We are going to talk about this in great detail in the next lab. So what we do is for thin specimens, we use the same indenters except use much lower loads. So T scale is for thin specimens, uses same indenter as B scale, which is what we are going to use today. And N scale uses the same indenter as C scale for steel and harder alloys. Now there are other scales for special purposes that we can use, such as plastics, etc. So this superficial Rockwell hardness test, we call it for thin specimen, we call T scale, which is what we are going to use. It corresponds to Rockwell B scale, uses the same ball indenter on the left, and N scale on the right uses diamond indenter, corresponds to C scale. So in superficial Rockwell hardness, you will see in the video, we apply first a minor load. The minor load is 3 kgs to seat the indenter and establish reference for depth of indentation. Then we apply either 50, 30, or 45 kg load. That's called a major load. And we select this load to make sure that we don't have any deformation on the back side of the sample. And we want to keep the indentation depth less than 10% of the thickness. So what the machine does is, as it applies this 15 kg load, it measures the depth of indentation. And that depth of indentation is converted into a hardness scale. So the scale does not specify the test. We need to specify what load. So if we have T scale with 30 kg load, we'll say hardness Rockwell 30T is so and so. So either we use this as a subscript or we use it longhand like this. So let's see a video on our testing. Good afternoon, folks. This is our Rockwell hardness tester. It can also do superficial Rockwell hardness testing. This Rockwell hardness tester is made by Clark. It is model CR3E machine. I'm going to switch on the machine. The power button is in the back. It takes about 20 seconds to initialize. I want to measure the hardness of this Tensile specimen. It is made out of 6061 aluminum, a soft non-ferrous alloy, and you can see that the specimen is quite thin. If I were to make a regular hardness Rockwell B measurement on it, the large load of 100 kg is going to punch the indentation through, and I would be able to see at the back of it. So I cannot do a regular hardness B testing on it. I'm going to do superficial testing. So the superficial scale is T scale, and I have a 1/16 inch ball indenter already. So I'm going to use 15 T scale for this. So I want my major load to be 15. And it shows me the scale of 15T. If I wanted to, I could scroll this scale to different units, 15x, 15 so, but I want 15T. Also, I want my minor load to be 3 kgs, so I rotate this holder, which is a dial, and this shows S here for superficial scale. So I am all ready to go. I have the right indenter, I have the right minor load, I have the right major load, I have the right scale on it, and I'm ready to make a hardness measurement. So I raise the anvil, and again I'm going to keep raising the anvil till the LED buttons go and reach the set scale. Once it reaches the set scale, I let go. It applies the load, dwells, removes the load, and shows me the reading. So right now the reading is 36 on the 15T scale. Now I'm going to unload. So I'm going to turn the anvil counterclockwise, lowering it. I unload and I have an indentation. It is barely hard to see. We will see how it looks in the video. Thank you. Okay, so next thing what we are going to do is we are going to measure this 15T Rockwell hardness along the failed tensile specimen. So you can see these pen marks. My resolution is not high enough that you can see the dots. And then what we are going to do is we are going to measure the length of each of these two halves and subtract those positions so that we are measuring distance from the failed edge. So we need to measure the length of these two halves. And then we are going to plot hardness versus position. We are going to compare the curves for red and green specimens and see if they correlate with our tensile curves. And then we are going to evaluate our results, make summary conclusions. Okay, so let us consider I have made the hardness test, entered them into the spreadsheet. So here is our template. Let me fire up my spreadsheet. So here is my spreadsheet. We just did a work. Let's hide all these rows. We have already done those work. So I'm going to hide rows. Okay, I don't want that. So I measured the half using a ruler. So this is my left half, this is my right half. Left half comes out to be, this is my notation. Exactly 5 inches. Right is 3.668. For the green sample, left is 5.044 and right is 3.736. Okay, so I have red, I have done green. So let's start processing. So I am going to maximize this. So we want distance. First of all, we want 3 digits everywhere because our precision in measuring with vernier caliper was thousandth of an inch. So what we are going to do is we want to measure distance from the failed edge. So we are going to take this value 5, which is our length of the half. And we want to always consider this length. So we are going to put $sign in front of them. Minus the distance from the left edge. And we are going to copy this down for the left half. We are going to do the same thing for the right half. Equal to, take this value and F4 minus distance from the right edge. So you're going to copy this down. Okay. Oops. These were 3 digits, right? So we are going to do the same thing for the green sample. Left half length minus distance. Copy this formula for left half. And then for the right half. Okay, so now you're going to learn some nice tricks. So let's collect these four columns: red X, red, green. X is x-axis, remember. And we want to insert a chart with dots. As I said, it's always a good idea to move the chart to a full worksheet. So let's name it plot 1. And since we always create the plot after the data, let's position it there. Okay, so let's look at, first of all, we have got 1, 2, 3 curves. We plotted 4 columns, we have 3 curves. But remember, let's select this one, top curve, select data. So that is our green curve, right? So if we edit it, what we want to do is we want to plot C versus D and E versus F. Right now, what it has done is it's plot DEF versus C, C on x-axis. So here is our series name. So we are going to call it green aluminum, and we want to do E versus E. So this is going to plot E versus F. Okay, we don't want any green X. For the red, let's also edit and give it a name, red aluminum. Okay, so now we have 2 curves, 2 sets. Also notice here our hardness values go from something like 20 to about 90. So let's format this axis, say 20 through 90. Also our x-axis, what we want to do is, it has got, first of all, too many decimal digits. So we want just one decimal digit. And we want to put values in reverse order because remember we are going towards the failed edge. So we want strength to increase or hardness to increase. So I reverse this order because then this is the failed edge. So this is how we plot stress strain curve typically. So that's pretty much it. Let's add our usual element chart. So we will say Rockwell 15T hardness versus distance from failed edge. Okay, let's do horizontal distance from failed edge. And remember, this was in inches. Y-axis, vertical. So this is Rockwell 15T hardness. Remember, it has no units. And finally, our legend, we want it on the top. And that's pretty much it. Right. So looks nice. Let's go for the data. Let's make sure our number of digits is proper. Remember, in our positions, we can't have more than 2 digits, right? Because that's our precision, measuring with a simple ruler. So let's do format cells, and we want 2 digits. Okay. Same thing here. Make sure we have 2 digits. 2 digits. Okay, folks, let's check, make sure we have our print set up. So we have portrait 100%, we have grid lines, row column headings. Everything seems to fit in nicely in a page. Oh, we hid rows here. So let's go unhide those rows. So we are going to unhide. Let's check again. File, print. So everything fits one page nicely. So we are going to save. So we always save as macro enabled workbook. So demo test. Okay, so here is our hardness versus distance plot. So remember, we are going towards the failed edge. So if you look at our red specimen, what we expect as we go from left to right, we expect hardness to increase. So you can see it increases substantially. So we see the effect of strain hardening. In green sample, we see pretty much the hardness remains pretty much the same. It does not strain harden much. But one thing we know for sure is that the green specimen is much, much harder than red specimen. We know that. This is annealed and this is precipitation hardened. Also, our hardness profile correlates with our tensile testing curve. So notice in our red specimen, we saw substantial improvement in strength as we deform more and more. So we saw substantial improvement in hardness as we deform more and more. Here the curve is rather flat. There is not much of strain hardening, and therefore we don't see much of that effect. Okay. So we just summarize hardness profile in the two tensile specimen was qualitatively consistent. Red alloy has larger potential for strain hardening. We saw a sloping curve. Then green alloy, which was a flat curve. We know green alloy is harder than red alloy because it is precipitation hardened. I'm not going to say everything. I would like you to think about more conclusions and discussion of results as you think about this data. All right, take care.